Michal בדקה את עצמי, מיכל I just decided on the grade. I just decided what the bonus is going to be. They're not so bad. The median grade was 80, so it's actually quite good. I think more than 15% got 100 in the last quiz, so actually a good achievement. Okay, so we're going to treat the ideal dosed fluid. We've done with the fermions, we've done with the electrons. The thing to remember about electrons is that as long as we are not treating a small system, okay, only when we are treating a small system something peculiar starts to happen. In all situations when we have a lot of electrons in a system, they will all pile up in the energy spectrum. They will all pile up one on top of each other up to the epsilon Fermi. And the epsilon Fermi is going to be proportional or to the number of electrons that we have inside the system. So the larger the number of electrons, or the larger is epsilon Fermi. Important are the electrons that are sitting in the vicinity of epsilon Fermi. Okay? And since epsilon Fermi is extremely large, we don't care about what's going to happen over here. We only care about what happens in the vicinity of epsilon Fermi. And that's it. So electrons are piling up on each other, on top of each other. We can consider them as free. And then the equations that we develop are sufficient actually to describe even complex systems. But there's a lot of research that's going on about strongly interacting fermions or strongly interacting electrons. We assumed in what we've developed so far that the electrons were non-interacting. So why people do investigate those questions, right? We have shown that it's not important, the interactions, because epsilon Fermi is extremely large. Right? So the answer is...
Can you repeat the question, please?
Okay, so we have shown that the interaction between the electrons is completely not interesting. Why it's not interesting? Since we assume that there is a Pauli exclusion, okay, so think about it in the following fashion. If we have two electrons, right, so this is the distance between the electrons, this is the interaction energy. Okay. So when there is no interaction, if the two electrons are away from each other, basically you can say, well, the interaction energy is absolutely zero. The potential, interaction potential. Pauli exclusion principle says, well, when they're really close to one each other, they cannot be exactly the same place. So there is some sort of a delta function over here. Okay? There is a delta function when the particles, so this is the R, if we have two electrons, let's consider that we have two balls, small balls, and this is the distance between the two particles. Right? Non-interacting particles basically says that they can be whatever they like. Okay? They can overlap. We don't really care because this particle does not fill the existence of the other particles. So this is what we mean by non-interacting particles. But Pauli expression exclusion principle, what it says is that when the particles are located exactly at the same point, it's an impossibility. So it cannot happen. If we try to understand this by means of energy, it's as if we have an infinite potential when R equals exactly to 0. Okay. So this is the interaction that we assumed when we treated free electrons. They were not exactly free. Okay. They were interacting, but interacting in the sense that the exclusion, we haven't thrown away the exclusion principle. Now, any interaction between electrons, for example, the interaction in Coulomb interaction, we basically add an additional potential on top of this one, right? So we have to add some sort of a, for example, this is a Coulomb potential, 1 over R. Okay? So they attract or basically push out each other with some force. Okay? So they are not exactly free. It's not only Pauli principle. There is also an additional interaction. Right? Now, this interaction is always, when R equals 0, it's always smaller than the infinity that we have over here. And here, there is a specific additional value of the energy that comes due to the interactions between the two electrons. Right? But this interaction, or the scale of this interaction, it's always much, much, much smaller than the Fermi energy. So basically, it means that, this is what we've shown, we can completely neglect this additional interaction energy between the two electrons. Right? We don't really care if it's there or if it's not, since all the scales of those interactions is completely negligible with respect to the epsilon Fermi. We don't really care if there is additional interactions or there are no additional interactions, or what form of these interactions there actually is between the electrons. This was the claim. Now, and here comes the question. There are a huge number of people who are doing research on strongly interacting electrons, okay, in condensed matter. A lot of this is connected to the quantum computing, but not only. Why it becomes important, right? So we have shown that it's not important that they're interacting. All of those systems that are actually under current research in condensed matter are electrons that we have to assume that they are strongly interacting. And the answer is that all those systems that people are usually looking into are small. The number of electrons or the number of particles in such systems is not big, is small. The moment the number of particles is small, epsilon Fermi goes down. And then the interaction becomes comparable to epsilon Fermi, or sometimes even larger than epsilon Fermi, and everything what I have taught you becomes not so true, right? So all what we have discussed is only in the limit when we have a lot of particles such that when they pile on top of each other, they're bringing a huge epsilon Fermi. The moment that the number of particles is small, epsilon Fermi is not so big, and then this additional interaction energy becomes extremely important. So this is electrons. But now we're going to bosons. For example, not bosons, but qubits in quantum computation. There is not huge amount of particles in all those qubits. It's not big. Okay, so we have bosons now. And we are starting with a simple example. With 3 states, 3 energy levels. Okay. So remember, the fermions, what we have tried to treat initially, is the situation where we have only 3 levels, 4 electrons. Now we're doing exactly the same thing. Okay. So we have epsilon 1, and we have epsilon 2, and we have epsilon 3. Okay. And we want to compute the partition function. Right? Eventually the question is, what is the partition function? Z. For the fermions, remember, there was, when I was looking on the level epsilon 1, it could be either empty, so no particles at the level, or I could have 1 particle. But with bosons, because there is no Pauli exclusion principle, I can also have a situation when I have 2 particles sitting in the same level, or 3 particles sitting in the same level. Okay? there are no limit of the number of particles that can sit exactly at the same energetic level. So I need to go and compute sum over all states. And here I would have e to the minus beta epsilon minus mu n. Sorry?
Never mind.
Something else? Capital N? Right, capital N. The n is the total number in the system. Okay, so I need, and this is, oh, it's the total energy of the system. And I have to go over all the different states. Right? What is a state? This is a state. Another state that I will add a particle over here. This is also a state. Right? Now, the moment I can compute this z, I can do whatever I want afterwards. But the first step is how to calculate the partition function for the system. And the answer is always, we need to factorize over something. Okay? We always factorize over something. We do not know how to solve the partition functions if we do not factorize. At least in this class. Okay, so for fermions, over what I managed to factorize, over the different energy levels. I forgot about the particles. I couldn't care less about the particles. I managed to factorize over the different energy levels. So let's try and do exactly the same thing, but without the Pauli exclusion principle, and try to factorize over the three different energy levels.
Why can't we factorize over the particles, right?
Because the number of particles is
not constant.
It's something. Okay? And it haven't worked for the fermions. So you know, the guess is that it won't always also work for bosons. Great. So let's, for this system, let's write the general energy. So a general state, okay, so how I define state, I'm looking on this state. For example, what is the energy for the state that is now plotted on the board? So what do we have? We have 3 particles at epsilon 1. So we have 3 epsilon 1 plus 1 epsilon 2 plus 1 epsilon 3. Great. What is n? The total number of particles that we have in this system. 1, 2, 3, 4, 5. So we have 5. Now, I want to write this 5 a little bit in a different manner. I would write it as 5, not 5. So I would write it 3, that is related to this state, plus 1 and plus 1. Okay, why I'm writing this in this form? Because you see, I need to, well, beta is always something, 1 over k boson t, but I need to write this expression. So E minus n. For this specific example, what is going to be? It is 3 epsilon 1 plus 1 epsilon 2 plus 1 epsilon 3 minus, okay, minus 3 plus 1 plus 1. Okay. So I'm writing it down and separating it into 3 different expressions. Instead of writing this as a one big expression, I'm separating it into 3 different expressions. So it is 3 epsilon 1 minus 1, right?
To multiply by mu.
Mu, right. Mu. So it is 3 epsilon minus mu, okay, plus 1 epsilon 2 minus mu, plus 1 epsilon 3 minus mu. Okay. So for this general expression, I have 3 particles, the number of particles multiplied by this prefactor, epsilon minus my u, here 1, here 1. Now, I can ask you the following question. For a general state, how I'm going to generalize this expression that I've written over here? So in general space, I will have n1 is the number of particles that are now sitting in level 1, right? n1 multiplied by epsilon 1. Plus n2 multiplied by epsilon 2, the number of particles that are sitting on level 2. Plus n3 multiplied by epsilon 3. Okay. The number of particles is n1 plus n2 plus n3. Okay, so e to the minus mu n is going to be simply n1 epsilon 1 minus mu plus n2 epsilon 2 minus mu plus n3 epsilon 3 minus mu. Why is it helpful? Remember, I need to count over all the different states of e to the power minus beta e minus mu n. Now, instead of e minus mu n, I'm writing this expression. So it is a sum over all different states, e to the power minus beta. And here I have n1 epsilon 1 minus mu plus n2 epsilon 2 minus mu plus n3 epsilon 3 minus mu. Okay. I'm separating this into a multiplication of three different expressions. States e to the power minus beta n1 epsilon 1 minus mu multiplied by e to the power beta minus beta n2 epsilon 2 minus mu multiplied by e to the power minus beta n3 epsilon 3 minus mu. Okay. So the only thing that is left now is the summation over all the different states. But how I define a state? Exactly. A state is defined by this triple of n1, n2, and n3. Give me a specific n1, n2, and n3, and I can plot you how many particles are sitting in level 1, how many particles are sitting on level 2, and how many particles are sitting in level 3. So each state of the system is explicitly defined by n1, n2, n3. They are somehow related when I'm summing here this summation. We don't really care what n2 does not care what n1 is or n3 is. We don't care. We just simply sum over all different possibilities. Now, since this parameter is independent of this parameter and independent of this parameter, they're basically all those three expressions are independent. So we simply describe it as a summation over n1 from 0 to infinity e to the power minus beta n1 epsilon 1 minus mu multiplied by a summation of n2 from 0 to infinity e to the power minus beta n2 epsilon 2 minus mu. A sum of n3 from 0 to infinity e to the power minus beta n3 epsilon 3 minus mu. And this is factorization, right? This is exactly what we were hoping for, that all these different states of the system eventually are going to be described by the means of a state of one single energetic level. This is partition function of energetic level E1. So this is E1. This is a partition function of an energetic level epsilon 2. So this is E2. And this is a partition function of an energetic level epsilon 3. So this is Z3. And eventually, we reach this factorization formula, right? Now again, exactly like in fermions, we forgot about the particles because the particles are dependent or affect, not affect. We don't really care what happens to the particles, but we for sure know that the different states are independent. the whole system, it can be dependent because it's probably preferable. This state is less preferable than the state when all of those particles are sitting exactly at the lowest energy. This for sure is true, but we are going to obtain it mathematically from the multiplication of Z1, Z2, and Z3. So Z equals to Z1 multiplied by Z2 multiplied by Z3. Independence. Okay. What is Zi? So Zi for a general energetic level I, it's the sum, and I goes from 0 to infinity e to the power minus beta epsilon I minus mu, all of this to the power ni, right? And this is a geometric sum. The first summoned in this sum is simply 1 minus, and here we have E1 minus e to the power minus beta epsilon I minus mu. Great. So in total we can write that Z equals to 1 over pi goes from 1 to 3, 1 minus e to the power minus beta epsilon I minus mu. This is a general expression, and if now I want to modify the system to 4 levels, 6 levels, 27 levels, it doesn't really matter. The only thing that is going to be modified in this expression is what? The number of levels that I have over here. Yeah. No, the particles, we don't care about the particles because the number of the particles is not concerned. But we have obtained during this solution of ours that all the different states are independent. Not states, energetic levels. We factorize over energetic levels. When we look on the system, I'm forgetting to describe the system by the means of number of particles. Okay? I'm describing it by levels, energetic levels, and their occupation, exactly as I was describing the fermionic level system. Right? There, I forgot about the different number of particles. I'm looking at this state. Is it occupied? Not occupied. Occupied? Not occupied. And then we derive this Fermi level and etc., which was related to mu. Small addition. What will happen if in my system I have degeneracy? Okay. So I have epsilon, and I have epsilon 1, and I have epsilon 2, and I have epsilon 3. And now the different levels can be occupied with bosons with spin up and bosons with spin down. Okay. How everything that I have done so far is going to be modified. Yep. So if you remember how we solved this question for the fermions, we basically said, look, you can solve this as if you have fictitious epsilon 1 with the power of up, okay, that can be only occupied by fermions with up. So here we have epsilon 1, level epsilon 1, up, which can be only occupied by bosons with spin up, okay? And we at the same level can have epsilon 1 with spin down that can be only occupied by bosons with spin down. Now, we separate everything. All the different levels are independent. They do not talk with each other. They do not affect each other at all. Right? So we can write down the partition function for epsilon 1 up. Okay? And we can write down the partition function of Z1 with spin down. Okay. In all of this calculation over here, the spin, this is why it's called degeneracy, the spin is not affecting anything. Spin is not affecting the sign or the value of the energy over here. it's not affecting the summation that Ni with spins up or spins down can go from 0 to infinity. So Z1 with spin up is going to be 1 over 1 minus e to the power beta epsilon 1 minus mu. The same is going to happen to the partition function of the level that can be only occupied with bosons with spin down, right? It's also going to be equal to 1 over 1 minus e to the power minus beta epsilon 1 minus mu. So you see all of this, those partition functions for the same level, spin up or spin down, doesn't matter, but we have to count them twice. Okay? So each time that we appear it, we can write it down. We have to multiply it by the degeneracy, okay, or take it a power in the sign of degeneracy. So if the degeneracy of level I is GI, degeneracy of level I. Okay. So if here the degeneracy is 2, it can be occupied so that we have only bosons with spin up and we have bosons with spin down. Okay, so GI equals, for this specific system, GI equals 2 for any level. So it's going to be just to the power of 2. Usually no. But you can do the following. So you can assume that the probability of a boson having spin 2 or 3 or 4 or 5 inside your system is, this probability is very near close to 0. Okay, and then you say, well, my degeneracy is only 2, right?
We can say that GI is 2s plus 1. Right?
Yep. Yeah. It's going to be dependent on the model. Look, in everything that we do, we're modeling something because the system or the physics is more complicated, right? So if the degeneracy is 2s plus 1, we're going to use it as 2s plus 1. But sometimes we can just say, well, it's just simply 2, and that's it. Yes, but the degeneracy is not the spin. The degeneracy is how many spins how the spin is not affecting the energetic levels. Questions? Yes.
Why can't we just sum over all particles in the same energy level? Then get a single sum from 0 to...
You're going to get exactly the same expression as I did over here.
I'm going to get just 1 over...
No, because you're going to have to separate all the different particles.
Why do I have to?
Because the quantum state... Okay, so the question is, this is one quantum state, right? Let's forget about the spin up and spin down. Okay? So this is one quantum state, right? Does it differ from this quantum state?
No.
Yes. Yes. The answer is yes. And you have to count them. Okay? The short answer is yes. The moment that you have spins, you have to count them. Okay? Because think about the quantum systems. You write down all the particles and you write down all the different quantum numbers that are somehow related to your particles. So if one of the particles have spin up, you're going to write it into your wave function. And if it has a spin down, you also write it in your wave function. So you have 2 different wave functions in your system. Right? Yes? Yeah. This is epsilon. What was important in fermions? Right? Remember, what was the important quantity in fermions? Look, I'm trying here to build an analogy. I'm assuming that we all understood extremely well the fermionic case, and the bosonic case is some modification. It's slightly different because the partition functions are different, right? But the idea of how to develop the tools are exactly the same idea. We simply factorize over all the different states. Okay, so for fermions, the important factor was, is a state is occupied or not occupied? Now, why it was important? Because if it's occupied, we know exactly how many particles are there in the state. Only 1. If it's not occupied, it's always 0. In our case, for bosons, it's already different, right? Because occupation does not mean that there is one single particle sitting there. Okay? It means that there can be 2 particles, or 3 particles, or 4 particles, or 5 particles. So instead of saying, is this occupied or not occupied, we're looking on the average number of particles at level I. Okay? So this is the analogous quantity to the occupation number or to the occupation probability in fermions. Why I can calculate Ni? My system is composed of 3 states, 3 levels, right? How can I go and calculate the average number at state, let's assume that this is 1, at state 1?
With the partition function of only this level.
Exactly. Exactly. The moment that we found, so it's always the same story. The moment that we managed mathematically to show that all the different states are factorizable, I start to completely, I do not care at all about what happens to the other states. It is as if this is a separate system. I can treat it as a separate system, and the number of particles for this state does not affect the number of particles at this state, and it's not affecting the number of particles of that state. The total specific state of the whole system is multiplication, yes. But when I'm treating one separately state by state, okay, I couldn't care less about what's happening in the other states. Okay, so what is going to be N1, or in general, Ni? So we do know that it's what? It is a sum from, not I, from Ni equals 0 to infinity, Ni multiplied by e to the power minus beta, Ni epsilon I minus mu divided by Zi. This is the probability. It's always like that, right? The moment that I know what is the partition function, okay, the probability it's always given by the Boltzmann factor, which is minus beta n I epsilon I minus mu divided by Zi. And the different states of the energetic level are defined by the number of particles that are sitting inside this level. Right? So we need to compute this part. Yes?
But when you look at the whole system, you say that you don't care about the number of particles.
Exactly.
So why do we have to...
So the thought, no. So what I said is that when I'm looking on this specific not state level, I don't care how many particles are sitting at the same time or can sit at the same time on the other levels.
Oh.
Right? But of course I do care about the probabilities for 3 particles sitting here and 4 particles, they do affect by the number of particles. Mm-hmm. That's of course because Ni over here, it will defines the states, different states of a specific level. Okay, so what it is, this guy over here. Alright, so Feynman trick, right? Feynman trick. So what we are having over here, right? All of this is always this Feynman trick. We have to take a derivative with respect to something such that we will get an Ni over here. How? Okay, so what you suggest something else. What your suggestion? But this is exactly the same. So there is deep side to d something, and if you remember this something, is going to be n or something like that. Right? So, but this is exactly the same thing. How we obtain this formula? We have taken this guy, all right? We found with respect we need to take a derivative, okay? And then we obtain this formula over here. Okay? So well, with respect to what? If you forgot the formula and you are now sitting in the middle of the exam and there are 3 or 4 pages of different formulas, right? This is how it looks. With respect to what you're going to take a derivative.
Beta mu.
בטא מיו, אפסילון פחות מיו, משהו כזה.
Beta mu. Beta mu, ואז אתה צריך לחלק.
Just mu, alright, just mu, this is a suggestion. Let's try it out. Okay? So, this equals to a sum. We can take the zi always outside. I repeat this Feynman trick again and again and again because, well, it's actually very important to people who are going to continue into master studies, and you will start to see field theories. Feynman tricks and Gaussian integrals are the bread and butter of all the calculations. Okay, so what we have over here? So we have z outside, and you suggest that it is a d to the d mu, okay, of whatever stands over here. So we have e to the power minus beta ni epsilon I minus mu.
You also need to divide by beta.
1 over beta? Yep. And do we have a minus? We don't have a minus. No, we don't have a minus. Okay, great. So now we take everything out. So what we have over in the open part. So we have 1 over beta. We have 1 over z I. We have d to d mu. Okay, and then we have this summation. Wow, let's write it down a little bit slower. So ni goes from 0 to infinity of e to the power minus beta ni epsilon I minus mu. Okay. All of this is zi, yeah. So we have 1 over beta, 1 over z, d to d mu, right? And here we have zi. Okay. Now, this equals to 1 over beta, d to d mu of log of z. zi.
שזה בדיוק פסייקל. מינוס דיפרנט.
So it equals exactly to, if you remember all the formulas, minus d psi to d mu. Okay, so our zi is, yeah, I deleted it, but I remember what it was. So we have the following. Ni average equals to 1 over beta d to d mu log of 1 over 1 minus e to the power minus beta epsilon I minus mu. Right? We are taking the derivative. So we have 1 over beta. Yeah. Minus d to d mu, or d to d mu of log of 1 minus e to the power minus beta epsilon I minus mu. And what we have now, we're taking a derivative, so minus 1 over beta. The derivative is 1 over whatever stands over here, 1 minus e to the power minus beta epsilon I minus mu. Okay, and then we take the inner derivative of this guy. Okay, so it is minus e to the power minus beta epsilon I minus mu multiplied by beta. Minus minus. You have minus and minus. Okay? Beta and beta cancelled, minus and minus cancelled. So we write this down as Ni. So this is the average number of particles. For fermionic system, it's exactly the probability of occupying an energetic level. But here it's just the number of particles. It equals to 1 over e to the power beta epsilon I minus mu minus 1. So this is for bosons. Yep. So it depends on the energetic level, it depends on the mu, which is the chemical potential, and it depends on the temperature. Now I remind you, what was the average number of particles that can sit at a single energetic level for fermions? Okay. So for fermions, it was almost exactly the same thing. Ni equals to 1 over e to the power beta epsilon I minus mu plus 1. This was for fermions. Okay. So extremely small modification. Minus to plus. Yes. This is the part of the bosons. You will see it's not why it's minus and here it's plus, but it's the physics of bosons and fermions are very, very, very different. And the mathematics of -1 and +1 actually describes this a very nice difference in the physical properties. We will see it by the end of the lecture. So, as you know, fermions cannot occupy the same state. Bosons can, and we see how it actually leads to this +1 and -1, and only this plus and minus are going to be extremely important. We will see why and how. Now, the first thing to notice is, so this guy is always positive, right? This is positive number, this is positive number, this is a plus. So this is always positive number. The total number of particles is always positive number. What happens over here? Great. When this particle, when this is going to be a negative, so I don't care if the average number of particles is around 0. It's fine. I don't have any particles over there. Nothing bad happened. But I cannot have a negative number of particles. Those are real physical particles. Right? They can come from the outside, they can be in my system, they can escape, but I cannot have -3 bosons inside. Okay? It's impossible. So since for the Ni, so this is for bosons, larger than 0 or equal to, we know that e to the power minus beta epsilon I minus mu -1 larger than 0, greater or equal to.
exponent.
Fine? Okay, so e to the beta epsilon I minus mu greater or equal to 1. Okay, so we always have to have the following quantity. Epsilon I greater than mu. And this is the opposite of what would happen for the fermions, right? Mu for fermions was the Fermi level. It's in the lowest temperatures is what is the highest energy that it can be inside the system. But for bosons, mu has to be smaller than any energetic level that is present inside the system. And specifically, if we have the ground state, okay, if epsilon 0 equals 0, okay, this means that mu is smaller than 0. Yes?
What about zero temperature? In zero temperature, you can have this equality and you can...
It doesn't matter. So this is always greater than 0. So t equals 0 does not exist, right?
So
Not exactly, right?
Zero,
So very, very close to 0. But t is always greater than 0, okay? And then you only care about the sign of this guy over here. You cannot reach the t equals 0. You can approximate it as closely as you wish, but you will never reach t equals 0. Okay? So you don't care about the sign of this guy. And this sign of epsilon I minus u have to be positive always. This means that epsilon I greater than u, and this is what happens. So if we have plus, Do you care about what's happening over here? This is a positive. This is a positive number. So positive plus positive, it's always positive.
לא, בסדר, אבל לא היה לך אילוץ על מיוט.
Exactly. Right? So in mu, there was a constraint. At t goes to 0, all the energies of all the different particles, of all the different states, have to be below mu. That's what we obtain. Here it's the other way around.
Can you repeat again the next sentence?
Yeah. So for fermions, this is the occupation, Fi, occupation of level, and this is epsilon divided by mu. And at t equals 0, it was a step function. Okay, this is 1. So all the different states were occupied only for the states that are less than mu. Right? So at very low temperatures for fermions, the energy, or all the possible energies, are only energies that are less than mu. Right? But this is a constraint that happens for fermions only for very low temperatures. For bosons, the constraint is the other way around. All the energies is above mu, and they don't really care about the low temperature or high temperatures. It always have to happen. Yes?
When you are using bosons, you have to prepare your system with energies that higher than mu, or they just...
The mu cannot be positive. There is no way to construct a system that can reach equilibrium, an equilibrium system, for which the chemical potential, so how much it costs to introduce a boson into the system, right? It's impossible to find such a system where mu is positive. That will cost you energy.
Oh, it's always negative?
It's always negative. Yes.
Is this a constraint?
And if it's not satisfied, the system cannot reach equilibrium.
Is this inequality a constraint on the EIs, epsilon i's, or
On mu. Mu is your parameter. How we derived everything in the grand canonical, we said we have a very specific epsilons, and mu and t are our parameters. So this is a constraint for mu. Okay?
We can't just choose mu.
If you choose mu, this constraint is not satisfied, everything falls down, and it basically means that the equilibrium conditions cannot be satisfied. Okay? It's not that you cannot construct a system that will live for a while such that mu is going to be positive, but it won't reach equilibrium. That's basically what it means.
איך אפשר לשפור לזה שמיו תלוי בטמפרטורה?
Mu, you will see. Okay, you will see how mu depends on temperature or not depends on temperature. Mu is a parameter. Again, t is your parameter, mu is your parameter. Okay, so what I'm saying is, this relation holds for any epsilon I. Even when I is equals 0. Okay, I equals 0 is your ground state. Okay? Now, if your ground state is exactly when your total energy is equals 0. Okay? So 0 greater than u. That's all. That's all I'm saying. If your ground state is such that the energy of the ground state is 0, your chemical potential has to be negative. If it's positive, well, it doesn't have to be negative. Okay?
מיו לא בדיוק פרמטר חופשי, נכון? אמרנו שמוצאים אותו דרך המשוואה של...
Well, no, mu is something. Mu is something. You can modify it. Okay? Remember, the number of particles was a free parameter, was something free. Mu was a parameter that it can be whatever you like. Okay? So when you say B or beta, my temperature is A, my mu is B, it's going to define you. What is going to define you? The average number of particles per level for the bosons or for the fermions. Alright? So when you say mu is A, beta is B, you know exactly what is the number of particles that are sitting on average for your state. What do you have done next for the fermions? So this is related to this next step that we have performed for the electrons. We said the following thing. Mu is important, beta is important, or the temperature is important, right? But what is more important in a regular physical system?
Pressure, volume.
The average number of particles. Okay. Because what I'm saying is, it's great that I can control the temperature and I can maybe control the what? The chemical potential. But I want it the other way around. I want to control the average number of particles and I want to control the temperature. Okay? So I'm taking like for the fermions, I'm taking a cube of a material. So it is L by L and by L. And I'm putting a lot of bosons inside this box. Right? I have a lot of bosons. Let's assume that our helium-4 is sitting inside. Right? And have a lot of different particles that are somehow floating inside, sitting inside. Okay, you're saying, Stas, you can control the temperature. Yeah, I can heat up or cool down the environment. And you can control something that is called what? The chemical potential of the system. So you provide the temperature and you provide the chemical potential, and then you know what is going to happen inside your system. Right? Now, physically, I want to do it in a different way. Yeah, I can control beta. This is very nice. So I can control temperature, can heat up or cool down. The other thing that I do want to control is the average number of particles. I do not want the system or the number of particles to go widely to 0 or to plus infinity. I want to say on average, this number of particles that I have inside my system is constant. Or the total number of particles is constant. Particles do not escape from here. I have this box, I put inside my helium, right? Those particles, atoms are somehow doing whatever they're doing inside my system. They are bosons, okay? And I'm saying that the total number of particles is constant. Why can I do that? Well, physically I always can, but mathematically, it's basically saying that when beta is prescribed and n is prescribed, they are defining the different values of mu. Right? So what physically happens is the same trick as we've done for electrons, for air fermions. We're saying instead of modifying beta and modifying mu, we take beta, the specific temperature, we take a specific Ni, and then we can find different mu's. Okay? So this is exactly the same trick, because when I'm talking to experimentalists, I don't want to explain to him about the chemical potential, and it has to be now A, afterwards B, or etc., etc. Usually I'm saying, put this and that amount of particles inside, keep the temperature at a specific value, right? And let's see what happens to the system. So usually what happens, I put a specific number of particles inside, I modify my temperature, I heat the system up, or I cool the system down, I look on the effect, okay? I look at what happened in the system, and mu is changing somehow. Because n is constant, temperature can be modified, and so mu is going to be modified, and it's going to be dependent on the temperature. Okay. Great.
Why can't you use the canonical partition function instead?
Because it's much more difficult. Because if I would tell you that the number of particles is constant, can I do this factorization trick? No, I can't. The answer is can't. This is the only why. So it's becoming a hard combinatorial problem. The moment that I'm saying, at the first place, the number of particles is constant, then I cannot perform this separation of different energetic levels, right? Because what I have done, I said, well, there are two particles at this level, and there are one particle at this level, and another two particles of that level. If the total number of particles is exactly 5, right? It's exactly 5. I cannot say that the number of particles here is independent of the number of particles here and the number of particles there. So all the different levels are correlated and they depend on each other. And I don't know how to solve it. Nobody knows how to solve it. The only way that physicists came up with is basically saying, let's forget about this assumption that the number of particles is constant. Let's assume that it can be anything. Let's solve the problem somehow. obtained the average number of particles, okay, and then said, well, this is a constant number, and do the math, right? So this is the trick. We're not assuming the n is constant in the first place to define the problem, to define the ensemble. We obtain a result, and inside this result we can say n is constant now. And the moment we say it, something has to happen to mu, which is fine. We haven't broken any rules. Great. So now that we know how to solve a system of 3 levels, we can solve a system of any number of levels, and we can solve the system of a boson gas inside a box, okay, where the different bosons, they do not interact with each other. So they are free particles. Okay, so this is what we are going to solve now.
רגע, סטס, אבל אם אנחנו מניחים שאנחנו עם כמות חלקיקים ממש מאוד גדולה, אז מה זה משנה לי חלקיק אחד כל החלקיקים?
You will see in a second. You will see in a second. The number of particles for, so the question is, would I care if the particles are not interacting? Why do I care about the number of particles at all? Right? This is the question. And the answer is, as if for fermions, we have seen that the mu, or the Fermi level, was dependent on the total number of particles. It's going to happen the same again for bosons. Okay? But it will produce a much more nicer effect. Okay, so we are now in the next half an hour. So let's try and solve the following problem. Boson gas of 3 particles. Okay, so we know that Z is a multiplication. I goes from 0 to infinity. Okay, because the number of different levels is actually can be, or has to be, infinite, of Zi.
זה אומר מספר החלקיקים אינסוף, לא? לא מספר.
No. What is here? What we factorized over?
Okay.
We all factorized over the energetic levels. So the total number of energetic level of a free system can be infinite. Right? I remind you that Zi is 1 over e to the power minus beta epsilon I minus mu. Minus 1 or plus 1? What it was there? Minus 1 minus. 1 minus. Okay, so it is.
ולדעתי גם אין מינוס באקספוננט.
לא, יש מינוס.
But there was a minus. There was a minus.
בעין הממוצע.
Yep. Okay. Now, moreover, we will have the degeneracy as G0 over here. So G0 is degeneracy.
Shouldn't it GI?
We're going to have the same degeneracy for all the different levels. Okay? It's easier. A little bit easier. Great. So, what is psi? Psi is minus 1 over beta log of Z. Okay. So it is minus 1 over beta, a sum. I goes from 0 to infinity. We have log of 1 minus e to the power minus beta epsilon I minus mu. Okay. Okay, so psi equals to, now we're going to use free particles. Okay, so they only have kinetic energy. And the energetic spectrum of free particles is what? Continuous, right? So if we only have energetic energies that are kinetic energies, the spectrum of those particles or those energies is a continuous spectrum. So we're having here minus 1 over beta, or plus, an integral from 0 to infinity of log of 1 minus e to the power minus beta epsilon minus mu. d epsilon, d epsilon. Because we are going from a summation, which is a discrete system, or the system of discrete states, and now we're saying, well, actually our states are continuous. Okay. What are the different d epsilon and etc.? Yeah. So we have derived it already. We derived it several times, so we'll just write it down. What are the different d epsilon is? So d epsilon equals the volume of our box that I just erased, divided by 2 pi squared, 2m h bar squared, 3/2 epsilon to the power of 1/2. Okay, how we obtained it? Epsilon is p squared divided by 2m, which is h bar k squared divided by 2m. This was the assumption, and h bar omega was equal to epsilon, and then we have took the d epsilon that we derived for waves, for Dirac, right, particles inside a box, and then we introduced this stuff inside the d epsilon, and this is what we obtained. This is the same expression for fermions too. Great. So now we have this expression of psi equals 1 over beta, an integral from 0 to infinity, log of 1 minus e to the power minus beta epsilon minus mu, and we have epsilon to the power 1/2 d epsilon, and on the outside we have everything else. So we have here psi, so we have 1 over beta, v, 2 pi squared, 2m h bar squared, 3/2. What is the next step? Next step is just to take this integral, right? So in order to solve everything, we need an exact expression for the grand canonical potential. And now, well, the only task that we are left with is to compute this integral. Okay? The moment that we know how to compute what is this integral equals to, we already know how to solve everything. Okay? So, how we proceed over here? So, psi is equal over 1 over beta, v by 2 pi squared, okay? 2m h bar squared, 3/2. And what we are left with here, so we can make it, or we can calculate it as an integral by parts, right? So we have a log of something multiplied by epsilon of something. Yes?
Shouldn't we integrate from mu to infinity?
No, why?
Because
What is my energy?
Because we assume...
What is my energy? So the lowest...
Yes, but well, we'll get...
Y minus mu, y minus mu. Can you have an energy which is... Can you have a negative kinetic energy?
Mu is positive too.
No.
Mu.
What are the limits of your kinetic energy? Forget about mu. Forget about mu. Your system is free particles that only have kinetic energy and they do not interact.
Yes.
What is the minimal energy of a particle can be?
0.
0. So we have to start from 0. What is the maximal energy of the particle that it can be? Infinity. So those are the two limits of the integral.
Mu has to be negative.
Mu have to be negative.
Okay.
Alright? Remember, we decide what the energies are, we will eventually decide what the temperature is and what is the average number of particles is, and you have to satisfy the equality. Okay? So if we take an integral by parts of this guy, okay? So So we have a log over here, and we have epsilon to the 1/2. What we obtain is an integral from 0 to infinity. A derivative of this log is 1 to the power 1 minus e to the power minus beta epsilon minus mu. Okay. Here we have epsilon to 3/2 d epsilon. Okay. Do you want me to solve exactly how I'm getting from this line to the next line? Yeah? Okay. Okay, so let's do it this integration by parts. So what is the integral of this guy? Is epsilon 2/3, right? To the power 3/2, okay, multiplied by log of 1 minus e to the power minus beta epsilon minus mu, okay, between 0 and infinity. Okay, and we have minus an integral from 0 to infinity of what? We have 2/3 epsilon to the 3/2 multiplied by the derivative of this log. What is the derivative of the log? So we take everything downwards. So it's 1 minus e to the power minus beta epsilon minus mu. Okay, and over here what we have? Minus beta epsilon minus mu. And we take a derivative with respect to epsilon. So it is minus beta. Okay, so first let's look on this expression. When epsilon equals 0, what we have over here? 0, we don't really care about what happened to the log, right? When epsilon equals infinity, what happened to the log? It's exactly 0. It's exactly 0. So we don't care about this part at all. It simply cancels out. If you don't see, try harder. Okay? You have to take the limit. You're right, the L'Hopital limit. You have to take a limit of this guy. Okay, so we're left with psi equals to minus 1 over beta 2/3 v divided by 2 pi squared multiplied by 2m divided by h bar squared 3/2. Okay, and what? Okay, so we don't have a beta over here. No, we don't have a beta over here, right? And this is multiplied by from 0 to infinity of epsilon to 3/2. And on the downside, we have e to the power beta epsilon minus mu minus 1 d epsilon. Yeah. Okay, so this is psi. This is psi. Great. Now we need to compute this integral. Okay. Now, it's easier not to compute directly this integral, but actually to compute what? The total number of particles that we have inside the system. Why it's more important to compute n? Because this quantity, we're going to say that it is constant, because we know what the number of particles that we have inside our box. So it's easier to compute n, and then out of the equation that we will obtain, say n is constant, let's see what happens inside the system. Okay, so we need to compute n, which is equals, as we already shown today, and if you remember, repeat the exercise, all right, with the phi metric, d psi to d mu. All right, this is what we have to take. No? Yes?
Yes, yes.
Yes, yes. Okay, great. So what we obtain, d psi to d mu equals to minus 2/3 v divided by 2 pi squared 2m h bar squared 3/2 an integral from 0 to infinity epsilon 3/2 d to d mu e to the power beta epsilon minus mu minus 1 d epsilon. And we have a plus over here. Okay. So what it equals to? 2/3 v over 2 pi squared 2m h bar squared 3/2 an integral from 0 to infinity epsilon to the power 3/2 d to the mu of this guy is 1 over epsilon beta epsilon minus mu minus 1 squared. Here we have minus 1 and then we take the derivative of this guy, which is e to the power beta epsilon minus mu multiplied by minus beta.
לא, בלי מינוס. בלי מינוס.
Why not? With respect to mu. D epsilon. Where? Here? Because what was an additional minus over here. Okay, so we have minus and we have a minus, so this is a plus, and then we have a minus from here and minus from here, and this is a minus. Okay, so you treat this a little bit more. Yeah.
You are calculating the minus side.
Where?
No, you said that the minus inside with the minus in the...
Is with the mu. So there was a minus, and we had a minus before. Okay, so it got cancelled out. It was a mu minus, it became plus over here. And then we have additional minuses from the derivatives.
לא, אבל היא אומרת שזה לא הנגזרת של פסאי לפי מיו, אלא זה פשוט n, הממוצע.
This is, okay. So I understand. This is fine. This is fine. Okay. So no. There, it's absolutely right. Okay, so you treat this integral a little bit more. Again, you can integrate it by parts, if you wish. I don't have time to integrate it by parts, but integrating by parts. What we obtain is that average n equals to G0V divided by 2 pi squared 2n divided by h bar squared 3/2 and integration from 0 to infinity epsilon to 1/2 divided by e to the beta mu epsilon minus beta epsilon minus 1 d epsilon. This is a much more nice integral. And now we're starting the fun. Because we forgot it was always over here. The general C always multiplied everything. Okay? It was always there. Okay, so next part is to calculate this integral. Now, the nice thing is that we call this 2 pages, don't worry, 3 pages. We call epsilon to beta mu zeta, so it is fugacity. I don't know what is the analog Hebrew expression, so this is the name of this guy. Fugacity. Say it harshly. Okay, and now we are going to, so all of this, this is fun, all right? But the only thing that is left is this integral, okay? So we have an integral from 0 to infinity, epsilon to 1/2, this fugacity to the power minus 1, e to the beta epsilon minus 1, d epsilon. Sorry?
It's Plitut.
What?
It means fugacity,
Yeah.
Plitut.
Plitut, all right. Fine. Fugacity. It basically e to the power beta mu. Okay? That's what it is. That's the only thing that matters. So everything else, it's not so important. This integral, let's see how we solve in general integrals of this form. Okay? So this is actually a little bit important. How we do this? You want all the prefactor? So this is A. So this is A, right? So all of this is A because it's not going to change. And we are going to solve this integral. Great. So the first substitution is epsilon equals x to the power 2. D epsilon equals to 2x dx. Okay? And epsilon and epsilon to the power 1/2 equals x. Right? So when we substitute all of this inside this integral, what we obtain is an integral from 0 to infinity. We have A, we have fugacity. We have fugacity from this part, right? So fugacity is over here. I write it down in a more nicer way. Okay. And what we have left is...
Isn't it to the power of -1?
At minus... No. So, do it like this. Fugacity. And here we have... instead of epsilon to the 1/2, we have x. Downwards, what we have is e to the power beta, okay, to the power beta of x squared minus 1, and we have 2x dx. And we have a fugacity, which is fugacity. Okay? That's the fugacity. All right. Let's continue. Yes.
Isn't the other integral is gamma times zeta or something like that?
What is this integral?
No, the one below that.
No. No. It's a different function. Okay? It's a different function. You will see in a second what this function is, but it's not a gamma. Okay. So let's transform this. Let's transform this into A. We have the fugacity over here. The limits are from 0 to infinity. From 0 to infinity. And I have x, or 2x squared e to the minus beta x squared 1 minus fugacity e to the power minus beta x squared dx. Okay. Now, the fugacity is a number which is smaller than 1. Okay. What I'm going to do, I'm going to expand this function, and I'm going to use a Feynman trick to describe what this guy is. The fugacity, the mu is negative. So 2a fugacity in integral from 0 to infinity. This guy is what? Minus d to d beta e to the power minus beta x squared. And this guy, okay, I'm just using a representation in terms of a sum. So this is a sum from n goes from 0 to infinity of a fugacity e to the power minus beta x squared to the power n dx. Okay. Now, let's take so let's try and describe this, or we want to basically, in order to solve an integral, you see now what we are going to have, we left with e to the power minus beta x squared. Here we have something e to the power minus beta x squared, but maybe some n over here. And the integration is from 0 to infinity. So we have a bunch of Gaussian integrals with the limits of from 0 to infinity, which is always square root of pi multiplied by something. So this is why I wanted to describe this as a sum. So the next step is somehow, okay, without asking mathematicians why it's actually can be done, take this infinite sum out of the integral, right? This is the next part. Okay.
Aren't we missing an x somewhere?
Where? This is the Feynman trick. This is the Feynman trick I got from here to here.
Okay.
Okay. I did a derivative with respect to beta. Okay. So we have 2a. We have a fugacity over here, and the next step is sum an integral from 0 to infinity. We have a fugacity to the power n. Okay. Oh, that's it. A sum, and from 0 to infinity. We have a fugacity to the power n. We have minus d to d beta e to the power minus beta x squared. Okay. And we have here multiplied by e to the power minus beta x squared multiplied by n dx. This is equals to 2a fugacity, an integral from 0 to infinity, a sum from n to 0 to infinity, fugacity to the power n. Now, what is this? This. Yes, so it's a derivative over multiplication of a function, or a multiplication of, okay, so it is 1 over n plus 1, right? 1 over n plus 1 minus d to d beta e to the power minus beta x squared, okay, to the power n plus 1. Right? Take a derivative of this with respect to beta. So we are going to have n plus going downward, so n plus and then n plus 1 is cancels out. A derivative of a polynomial of something to the power of n plus 1 is going to be this something to the power of n. And then you're left with the derivative of the inner part, which is the derivative of e to the power minus beta x squared.
Shouldn't there be a minus on that?
No. We have a minus. Okay? Okay. So, what we have, so it is 2a. We have a fugacity, we can take it now inside. And now I can also go and switch this guy, right? So I'm saying the following thing. First of all, this is n from 0 to infinity. Here I have a fugacity to the power n plus 1. Okay?
You can also change the
minus d to d beta of an integral from 0 to infinity of whatever is left inside, e to the power minus beta x squared n plus 1 dx. Exactly, and it sits over here. Okay? What is this? A Gaussian integral. That's very simple. So it's 2a, a sum from n to 0 to infinity, n plus 1 divided by n plus 1 minus d to d beta, okay, or of 1/2 square root of pi divided by beta n plus 1. And that's it. Right? Alright, so we have 2a, a sum n from 0 to infinity, fugacity n plus 1 divided by n plus 1. What we have over here is 1/2 square root of pi multiplied by 1 n plus 1 to the power of 1/2 multiplied by minus 1/2 beta to the power minus 3/2. Alright? What?
לא, אבל יש מינוס מדוד או בטא.
Something else?
יש את המינוס מהנגזרת.
And a minus over here. Right. So we have minus 1. Okay, so eventually, let's take whatever is dependent on n outside of the sum, because we still have the sum. So we have 2a minus 1 gets also divided by 4 multiplied by a square root of pi multiplied by beta to the minus 3/2, a summation, n goes from 0 to infinity. Okay. And here we have fugacity to the power of n plus 1 divided by n plus 1 to the power of 3/2. We are done. Yeah. No, but so we define this function. Okay. We define a function f3/2 of a fugacity. It's a special function which is a sum from n equals 1 to infinity, fugacity to the power of n divided by n to 3/2. In general, there is a special function f alpha. F alpha of z equals a sum n goes from 1 to infinity, z to the power of n to the power alpha. Those functions are tabulated. You can look for them in Mathematica. You can plot them. You can take derivative of them. There's a lot of different properties that are known for this f alpha. Okay, so sorry.
How are they called?
F special function f. They don't have a special name, very special name. And actually, I forgot how they call. They have a name. All right. So eventually, if we take all of this, we substitute what is a, what is the beta that we have inside, we obtain the following expression. So the average number of particles that we have inside the system is G0 V lambda t to the power of 3 f3/2 of a fugacity, while lambda t, or 1 over lambda t, it is a square root of m k Boltzmann t divided by 2 h bar squared, and this is called thermal wave length. Very simple and nice expression. When I was studying, it's actually ugly, you know, you have all of this, that's big and ugly. When I was studying on second year, I had a professor in electrodynamics. We had a quiz, and a lot of us got a huge and nasty, ugly expression, and one of us had taken all this expression, said, this is A, and then he described the final answer as f equals a multiplied by x, or whatever. The professor took 5 points from everybody, and when we came to complain and shown this exactly the same answer, he said, this is nice, and this is ugly. Physics is never ugly, right? So whatever you do, eventually what physicists are doing is they're getting a lot of different and ugly constants, and they're saying, oh, this is something nice, let's call it by a name, lambda t. Okay? Now, so let me take 1 minute so that you will be interested in coming on Tuesday. Okay. And I would like to plot to you this special function f of 3/2. Okay? So this is the fugacity. This is f 3/2 of the fugacity. And it behaves in the following fashion. It grows, it grows, it grows, it reaches a specific point, exactly at 1, and this value is 2.61 something, and then it becomes infinite. Right? So there is an infinite jump in this function. This basically is not defined for any fugacity that is larger than 1. Right? It's not defined. The maximum of this function is 2 to the point 61. It's limited between 0, right, and this 2.61. Okay, and it's undefined because it's actually performing an infinite jump for any fugacity that is larger than 1. So this is a forbidden area. You cannot be over here. And here comes interesting and physical question. So the maximum value of this guy is what? Is 2.61, right? So n has to be smaller than g0 v divided by lambda t multiplied by 2 to the power 261. Lambda t to the 3rd power. What is n? Number of particles that I put inside that box. Me. Right? I caught a lot of helium particles or whatever bosons that I could find, right, in my office. I put them inside the box. The math here tells me, Stas, you're limited in the number of particles that you can put inside the box. Right? Because this is the math that we got. And I'm telling you, okay, so that the limit that is provided by this formula is far, 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 far smaller than the actual number of particles that I can put inside the box. For sure, I can put more particles than this maximal value that sits over here. No matter what the temperature is, I can always put inside my box more particles than is prescribed by this formula. Okay? So this is the question, how it can be, right, that the math prescribed that there is a maximal number of particles that can be put inside the box, but in actual physical situation, I can put more particles because there is no limit, right? There is no limit to the number of particles that I can put. The particles are not interacting, they are bosons. There isn't even no Pauli exclusion. They do not care about each other. And yet, I'm getting something strange, that the total number of particles is limited. So what have been wrong? So there are two options. Either there is a very true and interesting physics that not interacting particles somehow limited, which is nonsense, or there is something else happening here, and in all this description that I have performed in front of you in the last 45 minutes, there was something wrong, right? And we will see what was wrong on what is right on Tuesday. Tuesday and Wednesday. Tuesday, we will finish bosons on Tuesday. Yes.
זה לא כזה, כאילו...